The first quantum phenomenon we're going to talk about is blackbody radiation. Any object will radiate electromagnetic radiation if it has a temperature, and since most things are above absolute zero, they're going to radiate electromagnetic radiation. This we call thermal radiation because stuff that's very hot ends up emitting electromagnetic radiation in the visible spectrum, which we see as this red glow on very hot things. Or as things get very hot, you see a blue flame or a blue star. The Stefan's law describes the total power radiated, and the spectrum of the radiation depends on the temperature and properties of the object, which is what we're going to go through next. So first, what is a black body? A black body is an object that can basically absorb all light. And so black bodies that you've seen every day are basically a hole. Your eyeball is a good example of a black body. Your iris appears to be black, and it's one of the few things that you see every day that is actually black. Your electronics that have black plastic aren't actually black, they're gray because light bounces off of them. However, your eyeball, your pupil, is actually black. If you actually do able to image light through your eyeball, then you're going to see red, which is why when we have flashes on a camera, you'll end up with what's red eye, and that's because what you're seeing is the blood vessels on your retina coming through the pupil as the light bounces back. So true black body absorbs all electromagnetic radiation and doesn't bounce any off, but it can emit electromagnetic radiation. So it doesn't reflect anything. The light that's coming off of it is actually emitted by the material. So here's a graph of blackbody radiation and the peak wavelength. So the wavelength depends on the temperature. So here we have 100K emits way down here, and it's not until we get into the hundreds of Kelvin and even thousands of Kelvin before we start getting radiation that we can see with our eyes. And the area under the curve represents the total amount of energy given. And you notice one very important part of this curve is there is a peak and then it goes down. So the wavelength of the peak is described by Wien's displacement law. So lambda max, this peak point, is equal to the product of that peak point times the temperature is equal to this number. And that's only the math we're going to do with this stuff because the mathematics otherwise get quite complicated. The ultraviolet catastrophe was one of the things that led to the invention of quantum mechanics. Basically, the ultraviolet catastrophe has a disparity between what a classic theory predicted and what we actually saw. So whenever we see this, we need to go back and revise our theories and try to figure out what's really going on. The classic theory basically says that if we take a string, right, it has certain wavelengths that are possible if we have two fixed nodes. And these wavelengths are dependent on the length of the string. But in theory, if on that wave we could get a very, very tiny waves, and then therefore we can fit very, very tiny wavelengths on the string. And so our string should be able to, in theory, vibrate at those very tiny wavelengths and do so at a very high intensity. That's not what happens, and so that's why this goes up exponentially. In theory, there should be no limit to how small we can go. But these short wavelengths, we predicted that there was an infinite amount of energy, which shouldn't sound possible. It's not possible. So at short wavelengths, what we actually saw was no energy, not infinite, but nothing. So this is called the ultraviolet catastrophe, where we predicted infinity but saw zero. Big problem for science that we need to solve. So Max Planck introduced the idea of quantum action, and he won the Nobel Prize in 1918 for discovering the quantized nature of energy. So Planck's resolution to this problem was that the blackbody radiation was produced by resonators, that instead of a continuum that we've shown here, we'll actually have discrete steps that we need to go through, and these are the discrete energy levels. So That's why h is called Planck's constant, that the energy of a given quantum number is equal to this constant times the frequency. And the key point is that there's quantized energy states, that this has to be an integer of some sort. And we can't have 1.376, we have to have 1 or 2 or 3. So now we're going to use that formula. Regal, a bluish white star in Orion, so not Betelgeuse, who's been in the news recently, but Orion, radiates with a peak wavelength of 145 nanometers. So we want to find the temperature on Regal's surface. That means we're going to rearrange this formula to solve for temperature is equal to this constant 2898 times 10 to the negative 2 divided by lambda max, which is the number given in the problem, 0.2898, 2 meters Kelvin, divided by 145 times 10 to the negative 9th meters, gives me 20,000 degrees Kelvin. So we wouldn't want to be there, but it is really, really hot. So blue stuff is going to be really, really hot compared to red stuff. And then we want to figure out what the energy of this light is. So we're going to use this formula that we've seen before, the wave equation and Planck's equation, to get the equation that E is equal to hc over lambda. I just took and solved this for F is equal to C over lambda and replace that F with that. That means, and we're going to assume that N is equal to 1, then we get 6.63 times 10 to the negative 34th is H times our speed of light, 3 times 10 to the 8th meters per second, divided by that 145 times 10 to the negative 9th meters, gives me 1.37 times 10 to the negative 18th joules, which is a really tiny number. So generally these tiny numbers we convert to electron volts. So that's that. As a second example, a little closer to home, is we'll use this idea that everything emits electromagnetic radiation, and where its peak wavelength is for these basically thermal imaging cameras that are able to convert those directly to a temperature. So here you can see somebody's grilling something in a hot pan, and we get that it's able to spit out the temperature without any contact. It's just looking at it. And these black pans make great black body radiation, and we're able to shoot it and tell the temperature. This is also how the non-contact temperature readers that we're seeing used nowadays. You can just point the thing at somebody's head and get the temperature. So here we want to figure out what wavelength of light we're seeing, because we don't see anything coming off the pan. So what wavelength is there? So lambda max is equal to this constant times 10 to the negative 2 meters Kelvin divided by the temperature reading. It says 448 Fahrenheit, which I've done the conversion to 504.6 Kelvin, gives us 5.92 micrometers, or 5,920 nanometers. So visible light goes from about through 200 to 700 nanometers, so much lower than what we can see. So this is infrared and not visible. The camera can see it, and we can have sensors that can be sensitive to that wavelength of light, but our eyeballs are not.